This video we are going to discuss about this chemical reactions of these oxytanes. So what are the different chemical reactions of these oxytanes? Before going further, let us compare these oxyranes and oxytanes. So oxyrane means three-membered heterocyclic compound containing oxygen, and oxetane means four-membered heterocyclic compound containing oxygen. So this is oxyrane and it is oxetane. Right. So what are the different things? So this oxygen is having two lone pair. This oxygen is also having two lone pair. If you see the basicity, this will be less basic and this will be more basic. The reason for this is, see here I have told this acts, if you see the reaction, it acts as sp2 carbon, right? So S character is more 33%. So it has more S character means it will be more near to the nucleus. Nucleus contains protons which are positive charge and neutrons. So electrons are more near to nucleus, so attraction will be more. So this oxygen is there, right? It will hold those electrons. So bases are the compounds which can give lone pair of electron, but here they hold the electron. So these are less basic we call. Whereas here it will be as sp3. So S character is around 25%. Compared to this, it will be less S character. So it can easily give the lone pair. So these are more basic. Here I am comparing only these two. You should not compare with these like compounds like this, right? These all compounds or these compounds. I am only talking about those two, right? So you have to concentrate on them only. So what we learnt, so this will be less basic and this one is more basic. So what makes difference in chemical reaction? Since it is more basic, so if I have any electrophile like this Cl, so what happens, this will be reaction will be more. So electrophilic reaction will be fast in case of this oxetane. So more how should I write? So it can easily react, or fastly I can call fastly they do electrophilic reaction, electrophilic ring opening reaction, right? Whereas this slow, the reason I have explained, right? These lone pairs are less basic, so they never give their lone pair easily fastly to this electrophilic ring opening reaction. So slow electrophilic ring opening reaction. So this is the first point. So I compared this basicity, and I using that I talked about this electrophilic ring opening reaction, which one will do fast, which one will do slow, right? So second point, this one and this one I am comparing. So here what is there, here more angle strain, and here less angle strain. Why? See here I have told it will be near to 60 degree, whereas this angle will be near to it, it will be around 89 degree or 90 degree, near to 90 degree, right? So both the case sp3 hybridization is there, no doubt. But chemical reaction, if you see it, it acts as sp2, but actually it is sp3, right? So it is sp3. So sp3 bond angle we know 109 degree or 109.5 degree I can call, right? So it is sp3. So 60 degree and 109 degree and 90 degree and 109 degree, so it is near, right? So angle strain is less, see here it is 60 degree, to get this 109 degree it is very far away, right? So here it will be having more angle strain. So what this angle strain does with the reaction, you may ask, right? That thing I am going to tell now. So what we understood, it will be having angle strain, and this one will be having less angle strain. It is also having angle strain, no doubt, but it will be less, whereas here it is more. So if nucleophile is there like this, so this can attack here and ring opening will be very fast. As its angle strain is more, ring opening will be very fast in presence of nucleophile. So I can call Fast nucleophilic ring opening reaction will be done by this three-membered heterocyclic compound. Compared to this, it will be very slow. The nucleophile attacks and then ring opening. Since it is less angle strain, it resists. This ring is very stable, so it resist the uh, ring opening reaction, right? So we need to add some drastic condition. What we do is we increase the temperature, right? Sometimes we carry out in drastic like HCl strong acid we may use, or sometimes photochemical reaction that we'll see when we talk about these chemical reactions, right? So what are the things we have studied? So let me summarize them. So first one is electrophilic ring opening reaction will be done fastly by this, then because it will be more basic, whereas nucleophilic ring opening reaction will be done very fastly by this because of angle strain. To get relief from this angle strain, they will do this nucleophilic ring opening and easily they will come out, right? This thing you need to remember, right? So these 2 points you mark it, right? So now let us discuss first chemical reaction, that is nothing but electrophilic ring opening reaction, this one, right? So the basics, everything, all idea I have given to you. So let us see that. So this is my Oxetane. So it will fastly do electrophilic ring opening reaction in presence of acid because it will be more basic. It gives the electron density and oxygen gets plus, and here OETH, like that I can write ethanol, right? So what it will do, it will do simply reaction like this, ring opening, and I'll get like this OET here, that hydrogen went, and here OH, other three carbons as it is 1 2 3, 1 2 3, right? So I got ring opening. This will be very fast, right? So if it is symmetrical oxytane. If I take unsymmetrical oxytane like this, then what happens? Similarly, first H plus, so no doubt I'll get this one, oxygen gets positive charge. Now I have got nucleophile, so HCl I am adding simply, so nucleophile will be Cl minus. So it has got two possibility, one is to attack here, other one is to attack here. Where does it attack, right? So this methyl is there. If this bond breaks, here carbocation is formed. That carbocation is not that stabilized by this methyl because only plus I effect is there. So plus I effect no much stabilization does to this positive charge. So this chlorine will attack from this only, this side it will attack, less hindered side. So it will do SN2 reaction, right? So less hindered side. So what the product we get, major product will be this one. Methyl will be like this, oxygen OH it comes, this carbon, and here chlorine comes. So this will be the major. Other product, if it attacks here, it can attack here also, but that will be minor. If attacks there, I'll get this one, chlorine here, CH2 and OH, and this will be minor. Instead of this methyl, if I have phenyl group, that we shall compare now, right? So just I will see, same compound I will take, but instead of methyl I will take this phenyl group, right? Phenyl means, so what is there, benzene ring it is like. So when I add HCl I'll get this one. So here it can break like this. If it breaks I'll get this one. So carbocation is formed, it becomes OH here, and this positive charge. So phenyl means benzene ring will be there. See here, let me draw like this. OH is here and here it is like this, right? So here positive charge is there, that will be stabilized by this pi bonds, right? Because of this stabilization it can form easily carbocation. And I have told, whenever there is formation of carbocation, it is through SN1 reaction. So SN1 reaction means the nucleophile. Here Cl minus is the nucleophile. It will attack to that carbon which is hindered, I can call, because the order will be tertiary, secondary, primary in SN1. Whereas for SN2 above here, it will be primary, secondary, and tertiary order. Sorry. Yeah, it's true. Right. So what I'll get? I'll get this product major here. So product I will write like this. pH here, chlorine here, other things as it is. So this will be major, and this one more product, if I want to write here, if this chlorine attacks here, then it opens here, this product will be minor. SN2 product will be minor, and the product will be like this: OH, CH2 and Cl, right? This will be minor, right? I hope I explained everything, right? Just you see it, right? And I have told this in heterocyclic chemistry, the book which I have referred, there they have given that this SN1 reaction is called as pull mechanism, and this SN2 book they have called as push mechanism, right? So you need to remember this. If they ask about pull and push mechanism, just you need to write the same thing, SN1 SN2, same reaction, you can write that, right? So next let us see one more reaction. Same thing, electrophilic ring opening reaction only. Same oxetane I am going to take. Here methyl is there, but here I am going to add this electrophile. What is this? Acetyl chloride, ACCl I can call, right? CH3COCl is nothing but acetyl chloride. So here lone pairs, it comes like this. Chlorine is good leaving group, lose the system. So I have got this one, COCH3, and Cl minus is there. So it will do SN2 reaction. Here oxygen will be having positive charge, right? So I'll get this product, CH2 Cl, right? Instead of writing all these things, we can simply write like this also, OAC, because that thing is understood, and Cl. So this is the product, major product, SN2 reaction. It will go through SN2 because here methyl group is there. So methyl group cannot stabilize that positive charge as good as that phenyl group, right? Or other O methyl or OH group. This will stabilize the positive charge more, because they will stabilize by this will stabilize by pi bond, this will stabilize by lone pair, but this methyl only stabilizes by plus I effect. So plus I effect not that important as resonance effect or that lone pairs, right? These things, these are the basic things, right? So further, one more reaction, electrophilic ring opening reaction, that is Friedel-Crafts reaction. Friedel-Crafts reaction. What is this Friedel-Crafts reaction? That we shall see. So I will add AlCl3, then I will add benzene, and solvent also is benzene only. We can write this benzene structure, or sometimes they will give C6H6. It is understood that it is benzene. So what happens here? Lone pair will be there, right? It is Levy's acid. So it will react with this lone pair and it will form AlCl3 minus, and oxygen gets positive charge and it is unsymmetrical, right? So further, because of this AlCl3, so the Friedel-Crafts reaction means it goes through formation of carbocation. So SN1 reaction. So only this bond is broken. So I'll get this thing here. See here. O AlCl3 minus, and this carbocation is formed. So here I have benzene ring, right? So what happens here? This benzene ring give its electron density like this. These all things, Cl3, and here I'll get like this. So here positive charge will be there, right? Positive charge here, and here one hydrogen, double bonds or double bond like this, right? So rearomatization is the driving force, because it will be anti-aromatic now. Anti-aromatic, benzene ring will be anti-aromatic, so rearomatization is the driving force. So this hydrogen will go like this, so minus H plus. So this step is nothing but rearomatization, right? So what I'll get this product. Instead of writing here, let me write like this only. So it gets its lone pair back and other things as usual. O AlCl3 minus, right? I hope you are getting it, right? So what happens? Just this hydrogen is there, right? So it will break simply here, Instead of writing this benzene ring, I can write pH with phenyl group and here OH. So this is the major product in Friedel-Crafts reaction, right? I hope you are getting, right? Instead of taking this, where is my compound, right? So instead of taking here methyl, if I take phenyl, so same reagent if I add, what I'll get? I'll get this product here. One pH here, one more pH here. The mechanism you are going to write by yourself. I hope you will get the same, right? So simply here the breakage happens and this benzene ring is there, right? That will react to this by giving lone pair, right? I'll get this product, right? I hope you are getting it. Further, one more electrophilic ring opening reaction, but I am here using carbon dioxide. So what happens here? Carbon dioxide, it will be electrophilic, right? So simply I'll write like this. C O minus here, double bond O. Anywhere you can write. So oxygen got positive charge. So this electron density it can donate here and this bond can easily break. So what I'll get? See here, like this compound. Just other things I'll draw as it is. O and here C is there. Double bond O, one more O and this, right. These three carbons are there and here. So total it becomes how many ring? 1 2 3 4 5 6. So it became 6-membered ring. So if I want to draw it neatly, I'll draw like this. All are same only, 6-membered, right? O O O, right. This compound I got, both are same only, just I wrote. If you write same thing you will get. See here also 3 carbon, 1 carbon, 2 carbon, 3 carbon. Here also 3, 1 2 and 3 and 3 oxygen, 1 1 1 1 and this carbon to this double bonded O, 3 oxygen, same compound, right? So these were the few this electrophilic ring opening reaction. Now let us discuss about this nucleophilic ring opening. Nucleophilic ring opening reaction, right? So let us see them. So that thing I have discussed. So here the nucleophile will easily attack because angle strain is more. To relieve that angle strain, this bond will be easily broken. Whereas for this cyclobutane, the reaction will be little slow because this is stable, less angle strain, because of which it is stable. So it resists the nucleophilic ring opening. So we use drastic condition to do ring opening reaction. So what are the drastic conditions that we shall see now? So let us see few examples. See here, this one, first example, right? To this I will add this CH3NH2. So NH2 acts as a nucleophile. So like this the ring should open, but to open this ring, if you see the reaction condition, it takes place at 150 degrees Celsius, so high temperature. Then only this reaction happens and I'll get this product. See here, OH is there, other things, 1 carbon, 2 carbon, 3 carbon and here nitrogen attached, NHCH3, right? So I got this product. So to make this reaction we need to maintain temperature about 150 degree, right? So high. Instead of this, if I take like pH, CH2 SH, same thing, lone pair will attack, open ring, but the temperature if you see it is see here, 10% of NaOH I have to use and the reaction goes for 6 hours. Then I'll get this product. See here, OH here, other things, 1 carbon, 2 carbon, 3 carbon and here S, CH2 and pH. So I'll get this product, right? Same simple reactions. So one more nucleophilic ring opening reaction is Grignard reagent. Right? So Grignard reagent. So what are the reactions that we will see? So here also we need to maintain this high temperature, right? First one is nothing but pH MgBr. pH minus will be there, right? So here it acts as a nucleophile. So second case we add water. Simple Grignard reagent reaction, you know. So it is pure SN2 reaction. So it will attack to unhindered site only. It never attacks here. No reaction like this because here no polar solvent is there, right? So it is pure SN2 reaction, right? That thing you need to remember. So what I will get, if it attacks here to this carbon, this will be opened, right? So I will get, see here, just OH here, and CH2 and here pH, this product. This OH, it came after this second step only. Initially it will be O MgBr, O minus MgBr plus will be there. When we add water, it becomes OH, and this MgBr becomes MgOHBr. Simple Grignard reagent reaction, you know those things. So I am going little fast now, right? So few more reactions let us see, and we shall conclude this topic. So here also I will add Grignard range MeMgBr, methyl magnesium bromide, and water I am going to add, right? So simple, this methyl will attack here only. I have told it is pure SN2 because no polar solvent initially. Then we add this water, no doubt, but initially we never add this polar solvent. The drawback also, you know, no need to tell again and again. So 1 carbon, 2 carbon, 3 carbon. So here pH is there, and here we will get OH. This is the product. I hope you know those things. So if we have 2 pH also, here no carbocation is found because water is absent initially, same substance. So here methyl, this will attack here, so I will get this product only. OH here, Me here, and this 2 pH. So I will get this product. I hope you are getting the same, right? So last reaction, that is nothing but photochemical reaction of this oxetane. Photochemical reaction. So what are these photochemical reaction, that we shall see now, right? So double bond like this, and here pH is there, at photochemical condition H nu, like this cleavage happens, right? This pi bond is broken, as it is, we know that pi bonds are loosely formed. This pi bond can be easily broken, so here we broke. And also carbon and oxygen bond can be easily broken, right? So we will break like that. So what we'll get, we'll get this product. See here, so radicals, let me show it by red marker, right? I have told oxygen radical will be unstable, so this is also unstable because oxygen can't hold this radical, as it is electronegative, and this here it will be unstable, so it will react like this, that bond is formed. So that I will show here. So double bond O, other things as it is, pH, and here one radical is there, and here one radical. If I write the same structure, just rearrange and write, see here, it will be like this, right? Other things, see, both are same only, no? So here also radical, here also, so now it can react, right? So the last final product will be 1 2 3 4, 4-membered ring it will form, and here double bond O adjacent to methyl group, and adjacent here to phenyl group, like this we get. So from oxytane, it happened this cyclobutane containing ketone group, right? Like this it happened in presence of photochemical reaction. This also we can call it as photochemical reaction or rearrangement reaction. Of this oxetane. So these were the few reactions of this oxetane. I hope you enjoyed this. In next video let us discuss one